I guess good afternoon. Well, it's almost afternoon here. 12:02, it's officially afternoon here in Washington, D.C., where it's like wicked hot. Welcome to day 3 of GASP. So far, we've had 2 afternoons of fantastic programming. We had a great workshop this morning with Isabella Velasquez on Quarto, and we're looking forward to another day and a half of programming. There is a detailed GASP program that's available online, and you can use this QR code, and I'll also put that in the chat. We're in the process of getting all of the presenters ready for our first session. So I'm going to kind of show you sort of the plan for the day. We've got, like I mentioned, we had the workshop first thing this morning. Then we've got 3 paper sessions and 2 lightning talk sessions this afternoon. There's going to be a short break, a little bit around 2 o'clock in the afternoon, and then we'll have announcements at the very end of the day. The sort of rules of the road, if you haven't been here or if you have and you need to be reminded, basically, if you want to submit a question, please do so using the Q&A feature. The real nice part about that is that then the speakers can also answer the questions within the Q&A. If there's time at the end of the session, then you can kind of go back and have a chance for that to be verbalized orally in the session, but at least you can get your question answered even if there's not time at the end. The chat is not enabled for the participants, but we will be posting materials in the chat throughout the course of the afternoon. In terms of accessibility, you should be able to access the closed captioning pretty easily. We are in the U.S. Eastern Daylight Savings Time Zone, UTC minus 5 hours. In terms of our sessions, the paper sessions, each of those papers will have 12 to 15 minutes, depending on how much time total was available in that session. And then the lightning talks, similarly, will have about 6 or 7 minutes each. The session chairs will moderate the Q&A based on available time, and they'll kind of call the shots on that. They'll be, keeping an eye on the Q&A and also other places. So if there's any problems, please contact Peter Meyer and myself, and one of us will be able to address it. At least we hope we'll be able to address it. So without further ado, I'll go ahead and pass the baton on to Clayton Knappenberger from the U.S. Census Bureau, who is chairing our first session on blending data.
Thanks, Lisa. So you actually covered a lot of what I was going to talk about, so I'll keep this really short, and in the interest of time, we can get right to our speakers. So we have a total of 75 minutes for this session. I'm asking speakers to stick to a 13-minute presentation. That will leave about 10 minutes at the end for questions and answers. Like Lisa said, please use the Q&A feature for your questions, and if you can also direct your questions to specific speakers or to the panel of speakers, that'll help me as we organize things at the end. So I think that's it. Let's just try to be patient with each other if there are any technical issues. Otherwise, Emily, I think you're first.
Great. Let me share my slides. Okay. There we go. So my name is Emily Gentles. I work at RTI, and today I'll be talking about some privacy-preserving record linkage methods. So first, I wanted to kind of discuss the difference between privacy and security. A lot of times, colloquially, we use these interchangeably, but they're not exactly the same. So privacy involves how data is used and controlled, while security is how we protect our data. So with privacy, this is using sensitive information responsibly, like removing PII from our data sets, whereas security is the actual measures that we take to protect from danger, threat, or harm, which is like using a secure environment such as FIPS-MOD. So privacy-preserving record linkage method is methodology that mitigates the privacy concern. In order to successfully do PPRL, you also need that secure environment piece. PPRL is beneficial when utilizing sensitive data, such as electronic health records, and it can help facilitate better data quality and accuracy while also capturing hard to reach or underrepresented populations. This allows for data to be used beyond the purpose it was initially gathered for, which is important when using data that's covered by HIPAA. And the main overarching goal of PPRL is that no party can obtain PII, which is personally identifiable information, that they do not already control. So nobody is seeing any PII that they do not already own. So taking a step back, what is record linkage? The basics is that you have 2 or more data sets that contain records. Here we're using people. And we're trying to determine which records in each data set are actually referring to the same entity. So here we see we have some name, date of birth, and address. They're pretty close, but there's a couple of errors, differences in the date or the month being put first, things like that. So we're trying to estimate, do these 2 records actually refer to the same person? With privacy preserving record linkage, we don't see any of this personal identifying information. So instead, we have these kind of black boxes that are represented by our cryptographic hashes or our tokens. As you can imagine, when we're not able to see any of the data errors are really problematic, and we need to clean and harmonize our data as best as possible so that we can have our good match rates. It's also difficult because if there are non-matches, you can't manually review them. So we need to address these problems before we match. One of the common ways to do this is something called phonetic encoding. This transforms strings into the phonetic parts and then encodes those parts, and it allows us to overcome differences in spelling, typos, in order to achieve better linkage. So you might have heard of SoundX. It's a really popular phonetic encoding algorithm. It's one of the best that's currently available, although it does have documented drawbacks. It's not equitable because we know that the quality of encoding declines for non-English origin words, and it's also susceptible to frequency attacks. An example of how this is great for matching is that these 4 different spellings of Sean are actually all matched to the same phonetic encoding, so we would be able to match these. There are a lot of alternative phonetic matching algorithms, especially if you have a specific language of origin that you're working with. An example of this is the Bieder-Morris phonetic matching. It's actually able to detect the language of origin before phonetically encoding. So it can detect that the German SCH sound maps to the S sound in the English phonetic alphabet. So it's able to overcome some of the differences in pronunciation. Another way that we match or overcome kind of spelling is the string comparators. So phonetic encoding is one of these types. We also have edit similarity. So at its most basic, this is the minimal number of insertions, deletions, or substitutions required to transform one string into the other. So if we have John without an H and John with an H, the edit similarity is 1 because we can just insert that H into that first John. One of the common edit similarity metrics is the Jarrow-Winkler. This edit similarity takes into account the fact that typos or differences are very common at the beginning of the word, and they're actually more important at that beginning stage. We also have something called trigrams, where strings are broken down into overlapping 3-character sequences, and the similarity score is calculated based on the number of matching trigrams and the unique trigrams. So here we have our example again with John and John. You can see that there are 7 unique trigrams, and also that we have padded the beginning of the word with blank spaces to achieve our kind of single J with a padding of 2 blank spaces. And they both share that J and that JO trigram, so their edit similarity is 2 out of 7. And here I'm using plain text strings for the example. In PPRL, obviously we are using these to encode and create our tokens. Another example of a string comparator is Bloom filters. So Bloom filters, like I said, they create mapping strings via hash functions into a bit array. So instead of using the entire strings or those trigrams we just talked about, they use bigrams, or a 2-letter pair that occurs sequentially. So we have an example with Jamie. We have 4 bigrams here, and each unique bigram flips a unique set of bits in the bit array. So like we can see in this diagram here. So we can create our field level Bloom filters, which are created for just one field. In this case, it would be the first name. And then we can also create record level Bloom filters where we kind of concatenate multiple fields into one big Bloom filter, such as first name, last name, gender, and date of birth. We can actually combine some of these methods. So if we use Bloom filters and phonetic encoding, we can improve our encryption step. So both phonetic encoding and Bloom filters alone are subject to frequency attacks. So if we combine these methods, we can get a little bit more of a balance between privacy and accuracy while mitigating those frequency attacks and reducing our computational burden. So here at the top, we see if I was just using a Bloom filter, I would have my different fields and I would just create that record level Bloom filter. If I'm going to use phonetic encoding first, I would phonetically encode my character strings that I can phonetically encode. Doesn't really make sense to phonetically encode something like female, male. So I'd phonetically encode that first and last name. I would then combine those with my numeric fields such as date of birth, zip code, and categorical gender. And then I'd create my record level Bloom filter from that. Now, the quality of matching produced from PPRL is difficult to assess, as manual review is not possible. PPRL systems should first be tuned using gold standard. Wouldn't we all love if those were readily available? So more often you're probably going to use public use or synthetic data sets that are relatively similar to your real confidential data that you intend to use. So by using synthetic or public data, you can allow for manual review and system tuning. And realistic synthetic data can often be generated pretty easily and it poses no security risk, such as the Cynthia. While setting up your linkage system, it's really important for your data partners to choose a validation metric to prioritize. Over here, I have a picture of the difference between precision and recall. There's also an F1 score, which is the harmonic mean of these. So your data partners need to prioritize what exactly they want from their linkage system. What is important to them? So now we're going to look at an actual case study where they did simulations for a bunch of these different string comparators. I have highlighted Bloom filters here since we looked at these. We see that for the true positive rate here on the left, that all of these string comparators are doing pretty well except for embedding, which we didn't talk about, but Bloom filters is pretty high up there. Then on the right, we see the runtime in seconds. So this is the scalability. We see that everything is doing pretty well. Bloom filters is not too bad, but that estimated edit similarity with something like J.R. Winkler is really struggling. It's taking a really long time. Here on the left, we have mutual information, which is a measure of privacy. We see that Bloom filters and trigrams are really providing good privacy protection, whereas embedding and that phonetic filter aren't doing as well. Then here on the right, if we're looking at the true positive rate by the mutual information, it's kind of just combining what we've already seen, that the Bloom filter and the trigram are doing pretty well. In practice, these methods are theoretically really interesting. However, they're currently very computationally intense. And there is a lot of research that's going on to make these methods faster. I think the talk after me, we're going to talk about speeding up record linkage itself. But in practice, it's more likely that a hashing algorithm like SHA-256, which is put out by the NSA, is being used. That's what most companies who are providing PPRL services are using, although they do have proprietary tokenization methods that improve on this algorithm. So that's the end of my talk. Thank you so much for listening. Here's my email, and this QR code will take you to my LinkedIn, and I'd be happy to connect and talk more about this. Thank you.
Yeah, thank you, Emily. So we're really good on time. Alex is up next.
Yep, great, thanks. We'll just share my screen. Okay. Okay, great. Thanks, everyone. So yeah, I'll be continuing on with the record linkage theme and talking about a new package that I've been working on for geocoding. So as most people will be aware here, working in the public area, data linkage is really critical for a lot of data science projects. So In my case, I've been working with cancer risk prediction. We need to really bring together data sources from different parts of the healthcare system in order to get a really complete picture of how people are interacting with it. So this could involve GPs, hospitals, and cancer registries. And once we have that data, we can start to do some interesting work with the modeling. But the data linkage is really a key enabler of this. So as Emily has just described, so the problem we're looking at is how to associate elements from one data set with elements from another. In this case, we've just got some synthetic data with a name and address column, and the data linkage problem is to be able to associate these together. And this is hard because of data quality issues. There can be spelling errors, abbreviations, missing information, and also incorrect information, particularly with addresses. So geocoding as well we can think of as a record linkage problem. We've got a standardized data set containing latitude and longitude values. So when we get the standardized address, we also get those. So the question is, hasn't this already been solved? So there are a lot of commercial options out there, like Google's geocoding API and similarly from Microsoft. But all of these have limitations. So if you're working in a very locked down environment, privacy is really important. We'll be concerned about speed and need to do it quickly. And also just, preferably we want something open source that we can use freely. So why don't we build our own? And as Emily has just mentioned, there's a trade-off in any sort of record linkage between accuracy and privacy and scale. So generally with when you're better at one, you sort of compromise the others. One of the key ideas to achieve scale is through the use of so-called blocking techniques. So we could naively search through every single address between our input and our address data set, but that might involve several million comparisons. So the idea is that we want to reduce our search space into blocks consisting of candidate addresses that are likely to be good matches. And then within each of those blocks, we can apply the string similarity functions that we talked about previously, so we can get an idea of which are the most promising matches. So this is another technique that I learned about a few years ago. I'm not involved in any of these papers, but it's quite interesting. Think of it as a kind of signature-based approach. There are a couple of papers. One's focused on geocoding itself, and one more on the general linkage problem. And the idea is that street addresses, like a lot of strings, generally contain a lot of redundant information, and we can understand this colloquially. Often when we're referring to a particular place, we don't use every piece of information that's in the official standardized string for that location. We often just use a small snippet. So if we take this input address here from South Australia, and we do some initial cleaning, converting to uppercase, removing non-alphanumeric characters, and we focus on this particular substring here. So these pairs of consecutive tokens. We can ask ourselves how many addresses in Australia contain this phrase. So there's a unit and a building number. And the answer is 4. And so this particular phrase acts as a useful blocking key or kind of signature. And that means if you've got spelling errors in other parts of the strings, it doesn't really matter so much because you've already got a really good way of matching candidates based on this small amount of information here. So the next question is, well, isn't this, I mean, this is kind of a contrived example. Like there's, these are quite high numbers in terms of street addresses and units. Most buildings won't have like over 200 units in them. And that in some ways is true, but it actually turns out to be, if you look at least for Australian street addresses, I assume this is true of many addresses around the world, that the proportion of these so-called phrases that contain, that appear with a certain frequency across the data set, you can see often, so around 90% of phrases occur fewer than 100 times. So it's actually kind of characteristic of a lot of street address data. So the idea of the algorithm is you create an inverted index. So we convert our input addresses, we separate them out into tokens. From each token, we associate with the original address. We do that the same with the reference data set. So another inverted index. And then we join these two tables together. So we can see based on that, on the tokens, which act as our blocking keys. And it turns out you can, in roughly 10 SQL queries, you can come up with a pretty good geocoder that implements this algorithm. So it's one of the nice things about this paper. When I was learned about this, it was during COVID, and we basically had 4 days to come up with a solution. So fortunately, in the appendix of one of these papers, they provided that. So implementing this algorithm, one of the key requirements, I think, from my perspective, I think from a lot of people who are using Python or open source tools, is you want to just be able to experiment with something quickly to be able to, in the case of Python, do a pip install. And DuckDB I've found is a really good tool that allows you to, has a wrapper for Python, and you can write SQL code. So it's very fast. There are APIs in Python and R. You can use SQL. It can be installed with very little fuss. So you don't need to have to set up a server instance if you, for example, work in comparison to, say, PostgreSQL. So here's some example of the code. GNAF is the Australian official address data set. So you can just, if you haven't used DuckDB before, you can query using SQL files directly on your hard disk, which is nice. You don't have to set up a server. So if you want to select, top 10 addresses from this data set, it's just one line of code. I'm not sure if I've got time for I might skip the demo, but basically you can try it for yourself. So I'll provide some details at the end of the package. And it's, despite the simplicity of the algorithm, it works quite well, and you can do some additional enhancements to improve the performance. And so the reason you might need this is because sometimes if you've got errors in the blocking keys themselves, then you can miss common spelling errors. So if we consider these first two tokens as a blocking key, if you've got errors there, then you're not going to get any matches because you're not going to be able to match with any of those blocking keys. And so the solution is what I'd refer to as sub-token phrases or trigrams, as was discussed in the previous talk. So rather than using full text from each tokens, you split them up into sub-tokens and then consider pairs of these sub-tokens. So this increases the storage size of the databases and reduces the speed, but increases the accuracy. And a nice approach is to combine these so you can filter out addresses which don't get geocoded using the faster algorithm can then get sent to this second character bigram or trigram phrases algorithm. Here are some results. There are always caveats I find with geocoding results. I'm struggling to find really good validation data sets online for how we actually benchmark geocoding algorithms. So I've been using a residential address data set and also a retail address data set to compare the accuracy at apartment, house, street, and suburb level across these. So Google wins, unsurprisingly, but this package Whereabouts, which I've been working on, is still quite competitive. So I'm not really familiar with US address data so much, so I'd be keen to hear from people here and learn more from people at the conference, what their recommendations for. I've been doing a bit of work in trying to build these databases, the geocoding databases, the inverted indices for US data, but I'm not sure the best way to approach that. And I'm still doing quite a bit of cleaning, so keen to learn more. If people are interested, I'm happy to talk. And yeah, that's Whereabouts. So if it's a 2-line installation. I've created a US California small database. Again, it's very tentative at this stage because I'm not as familiar with US data, so I'm not sure how. There's probably a lot of errors in there, but you can try it yourself online on Hugging Face. You can contribute to the project. I'm definitely welcome contributions. And yeah, and some acknowledgements. So thanks to the organizers for the opportunity to present. Thanks to the many different government agencies around the world who make address data available. It's very, the huge amount of work that goes into collecting and curating it. Yeah, and a few people, field government departments as well, that have really enabled this project. Thanks very much.
Great. Thank you, Alex. I don't want to jinx it. We're doing pretty good on time, so maybe at the end before Q&A, we can let you do that demo. In the meantime, though, let's move on to Tyson.
Hey, thanks for having me, everyone. I'm going to go ahead and share screen. My name is Tyson Weister. I work at the U.S. Census Bureau in the Center for Enterprise Dissemination. So we are the area responsible for data.census.gov. We develop that through an agile development process, and that means that we push system enhancements often. So what I'm here today is just to showcase some of the latest work that we've done to integrate and add functionality for visualizing data from the vast amount of information that's available at the Census Bureau. And this is the public website or the primary platform to get data from the Census Bureau. So I'm going to be showing a live demonstration for most of my 13 minutes. If you're not familiar with data.census.gov, we launched in 2020. We are the primary platform. It means that we have data from the most popular Census Bureau surveys and programs. We collect data for over 130. What you'll find on our site are, of course, data from the decennial census, dating back to 2000, the American Community Survey to 2010, and economic census and selected surveys back to 2012. That's a high-level view of what's available on our site, and we have a very detailed listing with everything included up to date if you want to visit the link at the bottom. So with this vast amount of data, we heard from users about wanting to visualize the information and digest the information more quickly in a more meaningful way. So in late December, we released the ability for you to take an estimate from any one of our 5,000 plus data tables on our site, and then you can create a custom bar chart, column chart or line chart for different geographies or other attributes that we'll show here. So I'm going to walk through the process from beginning to end with a very quick example, and then I'm going to move on to a couple examples after that just to show some additional chart functionality. I'm going to be focusing a little bit less on the step-by-step and a little bit more on what you can do with the charts and just kind of showing off the features and functionality. So to get started in our first example that we will walk through from beginning to end, we're going to map or chart out the percent of the population 65 and over for all counties in Arizona. And then after that, we'll show some more advanced chart features. So here on the live site, you'll want to go to data.census.gov. And I'm going to click the advanced search. So the first step typically to create a chart is to find a table that has data you want to make a chart from. I mentioned earlier, all of our charts are based on underlying data tables, so are our maps. So what you would do is find the table through one method or another. I'm going to use the filters. So under geography, click county, Arizona, and all counties within Arizona. And you just follow the process in the filter panel, clicking through different words and phrases. And then when you find something that you want to select as a final selection, you mark the checkbox and it will be adding it into the upper left. So you can do this for as many geographies as you're interested in adding to your chart. And then at some point you may select another search criteria. Here I'm going to choose populations and people and age and sex. So this is going to limit, when I run the search, to only give me the tables out of the over 5,000 we have on our site to the ones that are relevant to age and sex. And it's going to include that geography selection for all counties in Arizona. So we have both of those loaded here in the upper left. We'll run the search. And you see that new dedicated charts tab at the top. Again, I recommend previewing the table so you know what kind of data you're working with first. Here, S0101 has age and sex. And when you scroll down a bit in the table, you'll notice first very detailed age categories up front. But then eventually there's a row in the table for 65 years and over. It tells us our first county in Arizona has over 10,000 people, 65 and over, and that's 16.2% of the population. So we've been providing this information through tables and maps, and it's harder to digest large amounts of data. So that's why we introduced the charts functionality. So when you're ready to chart data, you'll want to click on the chart tab. Make sure you click on the left on the data table that you want to make a chart out of. And here is where your chart starts generating and you can customize what you're seeing. So at the very top, you'll want to tell the system, out of all of the estimates in that data table, which one do you want shown on the chart? It's very easy to do. Just click that drop-down menu at the top for the measures. And you'll notice that they're listed in the same order that the data rows were in the table. So you scroll down a bit, get to 65 years and over. And we do default these charts as well as our maps to percents if they are provided in the underlying data table. If you wanted to chart out total numbers instead, you could also switch the units. But I'll leave it at percent, choose 65 and over, and bam, our chart has been generated for us. It's sorted by the geography ID, but if you'd like to sort the information in a more meaningful way for you, you can sort it by the data value in ascending or descending order. And we can see very quickly in a couple clicks that La Paz County in Arizona has 42.2% of the population who are age 65 and over. Once you've done this, again, there's some more customizations options. If you prefer a column chart, we offer that functionality. You can add in the margins of error, so you can see the uncertainty around each of these estimates in the chart if you'd like to add that. We have a table view. When you click the button at the top, that will give you the estimate that you charted. So rather than having to download an entire data table with the population 65 and over, you can get just the one estimate here. And then we also not only integrate our data tables to make them chartable, we make sure that our charts are integrated with the maps. And what that means is if you click the map button at the top, the system's going to remember everything that you've done so far. So you're still clicked into the table. It remembers that you had selected 65 years and over, and we see this visually in an entirely different way just with that one click. So just another way to digest the information. Going back to the slides here, I wanted to take a moment to show some of the more advanced chart features. One of those, of course, is line charts. So these are available for tables and products at the Census Bureau when the table provides data across multiple years in the same table view. So all this to say, it's enabled for a handful of data tables. I wanted to take a moment to show you what it looks like here. And for this example, I already pulled up a search where I've selected a few different geographies, the US, Maryland, and the Salisbury, Maryland metro area. And then I selected a specific product from the American Community Survey called the Comparison Profiles that do provide data over time in one view. So I did some of that work already. I have the table pulled up here for comparative housing characteristics. And I can see this provides home ownership rates. So it says that 65.2% of people in the United States owned their homes in 2023. And I can see that data over time as I scroll through the table. And of course, all of my geographies are in the columns. So I found the table that has the data I want to chart. What's unique about this table that we didn't see in the last one is when you click charts, you will be able to create a line chart. The other charts are available as well, but when line charts are available for a particular table, we default users into that particular product view. And then we show the data over the time period covered by that specific table, which for this product is 5 years. And then again, just like before, if you want to change the value, we can go ahead and select the owner-occupied housing units to get the home ownership rate we were looking at in the table. Again, it defaults to the percent. And just like that, we can see the information much more easy to digest than we could in the previous view. So what you would do for this, when you hover over the different lines, it will show you which geography you're looking at. The reference year is the latest year covered by this particular chart, and you'll see that indicated with the diamond. So it's telling us that 60.8% of people living in the Salisbury metro area owned their homes, or 60.8% of households were occupied by homeowners, to be a little more technically correct. And if you were referencing that compared to previous years, you can see very quickly, well, this is on the decline. And if you were comparing that to the 2022 estimate from the American Community Survey, that number was 77.2% then. What's also unique about line charts for American Community Survey products is they include statistical significance. So our statisticians have gone through to do those calculations, and the way that we highlight that to data users, as you can see in the legend, is by opened and closed circles, where a closed circle represents statistical difference at the 90% confidence level compared to the reference year, and then the open circles represent no statistical difference compared to the reference point in that diamond. Last thing I wanted to show very briefly is additional functionality for our economic data tables. In those, you may have additional attributes you can add to the chart. So you won't see that in our demographic tables, but our economic tables are organized a little bit different in the data. So they have this additional functionality for the charts. So here is an example of a search I've pulled up. It has 3 geographies, and I've made my way to the county business patterns data tables. I've selected all 2-digit NAICS codes. This is an enormous table. There's 3,091 rows. And when you scroll to the right, you start seeing some of the actual data values provided through this table, one of them being number of employees. So if I wanted to look at number of employees across these different NAICS codes for the geography I selected, it is so much easier to do in the chart format. And again, what's unique is, well, first, what's the same is when you click the measure option at the top, you'll see the different variables from the data table, one of them being number of employees. So this is very similar process to what we've done up to this point in those other data tables. But what's unique is there are additional chart attributes where you could restrict the chart just to show data for number of employees in a particular industry, or you could even add all of the NAICS codes as a secondary attribute and see those charted out both by geography and by NAICS code. So you'll see total number of employees, and then it starts breaking it down for the different NAICS industries below. And then, of course, when you scroll through, you'll see the data for your different states. So that pretty much wraps up the new chart functionality. If you'd like more information, one resource that's available is we offer hands-on workshops where you can get some hands-on practice using the site, data.census.gov, the microdata access tool, and the API. We offer them monthly. They're free to join. And we have a resources page with all kinds of great educational materials and an email address where you can send feedback and data questions. And I look forward to answering any questions later today, but at this time, we'll pass it over to my next colleague.
Okay, thank you. I'll share my screen. Can everyone see the slides? Okay, great. Okay, thank you for having me. And I think this leads quite nicely on from Randy's talk. So there's probably a few parts in this that Randy has given a better explanation than I can today. Yeah, I'm here presenting some research done by Max Guinness, myself, and others at Policy Engine. We're a nonprofit focused on computing the impact of public policy for the nation and also in the UK. So I'm just going to start with a little bit of background about the different data sets that we have available to represent the US household sector. And there's a little bit of a problem statement, but generally this research is about how do we build a better data set that better captures all of the things we care about taxes, benefits, and incomes, so that we can better score policy reforms. So just a little bit of background. So a lot of the time when we're figuring out how much a policy reform affects the household sector or how much it costs, we might use the survey data sets in the current population survey. So this has really kind of rich demographics, program participation data. It's really representative of the US household sector broadly. But of course, as Randy mentions, it has various issues with it. It underreports income, especially at the high end, maybe also at the low end. And also, it doesn't really have all of the information that we need to compute someone's taxes. So some of the granular parts of the IRS tax filing forms, it does not have. It has good coverage of employment income and capital gains, but not everything. So that makes it pretty good for figuring out, how broad-based tax changes affect individuals in the US. But not the best. The IRS has admin data. So there's the public use file, which is a sample of administrative tax records. And that's often a lot more useful for example, figuring out how a change to the top rate of income tax affects individuals in the US, or how much revenue that might raise. The downside is that it lacks the strengths of the CPS, particularly around demographics. So we can't break down impacts easily by age band or state ID. And it's also a lot more locked down. It's not completely public. It is a proprietary data set that you can sort of buy access to for research, but it's not as open as the CPS. So we've got these two data sets. They are different and sort of some have strengths, some have weaknesses, tend to align with each other's in the negative correlation. And we need to figure out, how do we actually combine these to actually get a better estimate of the US household sector. So in terms of why this actually matters, accurate policy analysis is something that we hear about. We want to be able to figure out, how does tax and benefit policy actually affect US households? So taxes and benefits, we know, are a pretty big part of government spending and revenues. And we think that they actually jointly affects household decision-making. So we need a data set that is good at both taxes and benefits, captures the distributions of both of those, and it's also one data set rather than two. Because if you want to do analyses, we probably should be doing it on the same set of households. So that's the problem statement. And if we have that data set, hopefully we can get better policy by having a better understanding of what is the reality of the nation. So what we've been working on is essentially an open source enhanced version of the CPS that uses machine learning to combine the strengths of the current population survey and also the PUF. So if we think about what's good from either survey and try and find some way to combine these two, as Randy mentions, tax data has really accurate sort of observations of the relationships between, for example, employment income and long-term capital gains. But the CPS doesn't really have that. And if we look at what's good in the CPS has really kind of gold standard representations of demographics, SNAP participation, all of those kinds of things that we also care about. So what we do is we train an imputation model to learn the relationships between different forms of income and tax properties. We apply that imputation model to the current population survey. So for everyone in the CPS, we are predicting in an anonymized way what their capital gains, long-term, short-term, what are sort of better income imputations for people in the CPS that might more accurately represent the distribution of income. And then what we do after that is we're using machine learning to essentially calibrate the weights of the CPS in order to push them in the direction of more accurately representing the things that we trust more than we trust what we're getting out of the CPS. We know that household surveys have various issues. They're really great for a lot of stuff, but often they undercount benefit receipts, as well as undercounting the top end of the distribution of income. And so yeah, what we have made available is we think the first open data set with admin quality tax data, but also retaining the rich demographics and program participation statistical power of the current population survey. And all of this is open source and transparent, and we really welcome feedback. So just to sort of zoom out at a high level, and I won't go into all of this for time, we have a pretty multi-stage process going from the left to the right. So on the left here, you can see two building blocks. One is the CPS, the current population survey, and one is the IRS admin data sample. We age them up together. We use them to sort of transfer bits of information from one to the other. Mostly it's imputation. So training imputation models on properties and combinations of variables from one to another. So particularly from the PUF, we train a model to predict capital gains for employment income and apply that to the employment income that we have in the CPS. Once we have that imputation, we then calibrate the weights. So we gather a load of different statistics about things we know that are true. So for example, total amounts of SNAP spending and total income tax revenue. And we calibrate the weights of this to be consistent with those at the end of it. And right at the end, we end up with one data set that has imputations of income that we trust more than those in the CPS, and also weights that are calibrated to move us from being less inconsistent with total SNAP spending and total income tax revenues. So just to dive down into the details of the imputation and calibration methods that we use. So I think the standard approach for imputation is different from what we're doing here. Usually, I think a lot of the time we use matching for imputing, better estimates of incomes than we trust in the CPS. So that basically finds, one household in the CPS and says, can we find the closest match of this household in the admin tax data and copy the value over from that, which is great. But we found that it has the problem of when you have lots of households with the same demographic categories, they might actually have a really, really wide distribution of different values. So you might have the same households in terms of demographics, but massively different consumption or income patterns. So we use quantile regression forests. These are a variation of random forests that basically allows us to, instead of predicting one value, to predict a distribution of values, and we sample from that. So that means that we are sort of aiming to capture the really kind of chaotic variation that we often see in these household populations, even if they have similar predictors. And we've done some experiments to try and verify this is actually true. So for example, at the tails of the distribution, so if you predict everyone's capital gains for their employment income, if you just use matching, of course, you'll get the same number for everyone if they have similar demographic properties. And so at the tails of the distribution, your matching estimate might be really different from the extreme values that you also should expect to see in those. So we find that doesn't actually happen if you use quantile regression forests like this. On the calibration side, what we often see in these kinds of models is constrained optimization. So finding some set of weights that guarantees that the survey is within a percentage error for SNAP spending and income tax revenue and all of the other things that we care about. Which we tried first, and that is, it does do the job, but it leads to some sort of problems because a lot of the time you end up having some households with really high weight values. You might not want the survey to be really dependent on a few individual values. So we use gradient descent, which is a kind of more iterative process of iterate these weights, trying to reduce this deviation from statistics that we know are true. Until we get close enough or until we stop getting any closer. We also use dropout here. So randomly at different parts of this, we throw away about 5% of the households to sort of make sure that we're building weights that are resilient to some households being not part of the survey anymore, with the idea that then we're building weights where your survey that you end up with is not 100% dependent on a few individual records. And what we find when we put all this together is that we have a data set which is generally about as good or better than any one individual data set. So for example, infants, we'd expect the CPS to be really good at counting the number of infants in the US. We wouldn't expect the PUF to do that because it's not meant to be representative of infants. And we find that the CPS is pretty good, so is the eCPS. Qualified dividends. We find that actually the CPS and PUF can both be off. I mean, the PUF doesn't have non-filers, the CPS doesn't have really rich people, but the eCPS can sort of undercut both of these with the calibration. And we generally find that this new data set is generally better than definitely any one of the two across each of the targets that we care about. It also gives us metrics that seem sensible when we're measuring things like inequality. So for that, we don't really have a true value Like we can't just say, okay, here's the correct answer. So this is kind of more of an out of sample prediction, but we generally end up with estimates similar to the iOS data. And the real out of sample test is, what we're actually doing this for. So scoring policy reforms. Now, for example, Biden's proposed top rate increase to 39.6% at the top bracket. Treasury, of course, we're taking as the gold standard here, because it is. And the enhanced CPS we can compare to the original CPS. Now, we really wouldn't expect the CPS to be any good at this task, and it's generally not. But what we can see is that the enhanced CPS does actually retain the benefits of the admin tax data. And at the same time, it keeps this ability to be able to break down by demographic splits, which you can't do with the admin tax data. So trying to get the best of both worlds here, impute tax data from the admin tax data, and then also use calibration to get closer to the things that you trust. And then I'll just speak a little bit about, I think, the next steps, which is what we're working on. This calibration idea is great for national analysis, but it also opens up a lot of opportunities for diving down more local. I guess Randy's talk here is particularly relevant, but you don't have to just calibrate a data set to be representative of the nation. You could also do it for any specific local area. You could have an alternate set of weights for the CPS or the enhanced CPS for each individual, for example, congressional district or political constituency in the UK. And so that's what we've been doing. So in the UK, we've been essentially running this calibration exercise to build for every individual political district in the UK a version of our equivalent of the current population survey that is able to capture all of the income, tax, and benefits that we care about. You can kind of see here's a benefit reform that is generous for low-income families, and it is also generous for low-income areas here. So that's kind of reassuring as a sanity check. We have a online free web app, which is a direct interface to our model, policynation.org. So I'd recommend trying it out, where you can use this data set on policy reforms that you can build to kind of score, distributional, cost estimates, those kinds of things. So we hope that this is a useful tool for people, and you can see the difference between our data set and the original CPS. And we're also sort of building out some more interactive dashboards to try and bring the stuff that we think is in this data set that is useful to everyone else. So yeah, this is all open source. I think I'm out of time, so I'll kind of hurry up. But generally, yeah, we are working on expanding this methodology to dive down deeper into local areas, but also standardizing the different models that we've used here. So yeah, with that, thank you for having me, and I'll pass back to you, Clayton.
Yes, thank you. So let's go ahead and just jump right into the question and answer part. We have a bit of time for some questions, so thank you all. We have our first question from an anonymous attendee who is really interested in learning, I guess, more about what's going on with the increasingly mobile population with remote work after COVID. They mentioned that they operate out of at least 4 different addresses over the year, and they're wondering if that has any impact on record linkage. So this question, I think, can be open to really anybody. Do you want to weigh in on really duplicate addresses for what seem to be the same person? Maybe we're not noticing that. All right, well, maybe we can continue that conversation a different time. So we do have another question from Nora. She originally put in chat, but is now in the Q&A for Tyson, specifically about what kind of software was used to create the interactive dynamic.
Yeah, thanks for the question. That would be something I would need to check back with our development team and circle back to you to see if that can be shared. But appreciate your interest, and would be happy to connect on that.
Thank you. And we have, I think, a couple of questions for Nihal. I think one is really asking about whether we can try to validate, whether we can compare some of your imputations with restricted data. So Samuel says that his understanding is that CPS data are matched with W-2 and 1099 records, but you have to have access to those restricted data. So they're suggesting that we could compare your data to some of that restricted access data. Is that something that you've considered reaching out to somebody about?
Yeah, I think we'd be quite keen to do that. We haven't done that yet. Although I know that in the UK context, I think the UK government has also started doing that. And I think what they've found so far is that generally there's not that much inaccuracy with like people misreporting incomes or particularly benefits, which I think suggests that most of the problem is that the study isn't actually asking the right people rather than they're asking the right people the wrong things. So I think like I would expect that to be kind of similar in the US, although I could be wrong about that. I think it would be a good validation test either way. But I think even if we had perfect income values, like of course we'd still have that other massive problem of sampling bias, which could like also still be a blocker for accurate policy analysis.
And we have a second question for you, really about whether there's a way for users to measure the imputation variance with your imputations.
That would, yeah, that's something we should do, I think. Currently, no. I think, yeah, it would be very, very open for ideas on how to sort of practically do that. I think part of it is a kind of engineering problem where like, how do you do you build one data set and then like just sort of solidify that and let everyone use it? Or do you do more of the imputations kind of like on the fly and maybe like slow down stuff for everyone, but have more interactivity? So I think there's kind of both an engineering and also a an accuracy thing there. But yeah, definitely we're also very keen to, if people have ideas on how we could better handle uncertainty, especially at the local area. I mean, a lot of the targets at the national level, I think we find are super certain, like we're really confident in this SNAP payment. But at the local level, I think we see a lot more question marks on the data. So before we treat them as ground truth, they might be sort of worth thinking about that more. But yeah, I think that's a great question.
And I think that's all of the questions we have so far, but I have one for Alex. Alex, I know you're looking for address data sets for other countries. One that I was thinking of is the US Department of Transportation's National Address Database. Is that something you've looked at?
No, I haven't. I mean, I've looked at open addresses, but I'm not sure what, and there are a few different agencies. So I'm just not sure which is the official or which is the go-to, I suppose. So yeah, that would be, I would definitely be interested in
Sure.
having a look into that one.
All right. Well, I don't know that we have time for another question, but I want to thank all of our panelists. And I've really enjoyed getting to hear, I think, the full stage of really using blended data products. I think we've gotten, people who are working on developing open source tools for doing record linkage, folks that are working on protecting privacy of respondents through these record linkage efforts, practical applications where we can build new data products, and then also some discussion about how we can disseminate these new data products in ways that are better communicable to the public. So I think we're now going to move on to a lightning round, and I'll hand it back to Lisa.